the fun things about being an ecosystem ecologist, which is what I consider myself, is that you can study anything, because anything's in the ecosystem. And so if you get bored with one thing, you can just move on to the next thing. And so these days, I think a lot about soils. And so how many of you guys think about soils? Yes. Wow. So when you think about soils, what do you think about? Soil carbonates. Okay. What else?
Soil organic matter.
Soil organic matter.
Soil texture.
Soil texture.
Soil water.
Soil water. Clay layers. It's not just that stuff you sweep under the rug, right?
That's dirt.
It's not this stuff. That's dirt, right? We heart soils, right? Okay, good. No, so this is awesome. So a lot of people here really have a great feeling about soil. Do you think of it as home to billions and billions of tiny microorganisms?
Yes.
Do you think of it as the life support system for all of humanity because it provides 95% of our food? And it's definitely abused in a lot of places too. That's right. Do you think of it, I'm sure many of you think of it as a paleo archive of a lot of types of different kinds of climatic information and paleo-ecological information. Like this paleosol from Tasmania, which is actually thought to represent interglacial cycles from the late Paleozoic era, roughly 300 million years ago. And so there's a lot of things that we can learn about soils and learn about the world and learn about how to continue supporting humanity. And so here's my outline. You guys can see that okay, right? So I'm going to start out with a kind of overview on the carbon cycle. Most of my talk is going to focus on carbon cycle types of research. I'll go into soil organic matter. I have a section on soil organic matter, and that's the I Heart Soil little icon there. We'll talk about soil organic matter generally, and then also start focusing in on stable isotopes. And I have a couple slides on isotope tracers in the rhizosphere, which is kind of some newer work. Then we're going to go into the WTF section, what the flux, and so I do some work in soil respiration, quite a bit of soil respiration research. So there's going to be two sections. One is on the kind of the CO2 side, and then the other one is going to be on methane. That's WTF2. And then we'll wrap it up. So what motivates me to get out of bed in the morning is because I really am interested in how climate change and carbon cycling are interacting. And I'm sure many of you guys have seen diagrams like this. It's actually a little bit old. Now that arrow that from fossil fuel burning is closer to 10 or 11 petagrams per year. We know that CO2 is increasing in the atmosphere exponentially, about 1 or 2 ppm per year, as indicated in this record from Mauna Loa. It's long enough that you can sort of see that exponential increase, right? What are all those wiggles? Seasonality. What do you mean by seasonality? Winter and summer. Temperate forests, right. And so what are they doing? They're taking up the CO2 out of the atmosphere in the summertime and then releasing it back to the atmosphere in the autumn or winter time. All right, good. So you guys know a lot about the carbon cycle already, and we know that it's not actually very well balanced. One of the critical things that we're concerned about with soils is the soil, all the carbon stored in soils. This is the organic carbon stored in soils actually makes up more than the biosphere and the atmosphere combined. There's a lot of carbon in there, and it could potentially be quite vulnerable. So I'm sure you guys also know this, that the CO2 concentration in the atmosphere is well correlated with temperature. And this is, in case you can't see that, that's 400, goes back to 400,000 years ago in ice cores from Vostok, Antarctica. And this thermostat that is regulated by orbital parameters, the distance between the sun and the earth, the Earth's tilt and so on, It's regulated partly by ocean circulation and the sea ice extent because, of course, the oceans absorb a lot of CO2 out of the atmosphere. It's also controlled in large part by the terrestrial biosphere. And that's kind of where my work comes in. I'm interested in the feedbacks between the terrestrial ecosystem processes and the Earth's thermostat. So as we went over before, obviously plants are photosynthesizing, taking CO2 out of the air. Some of that organic matter turns into soil organic carbon and then it's released. Warmer temperatures stimulate rates of organic matter decomposition. This is an exponential effect, which can then amplify climate change. Rising atmospheric CO2, of course, in turn, stimulates photosynthesis. That's called CO2 fertilization, right? This could mitigate climate change. It's also temperature sensitive. And so a lot of the research that I'm doing is addressing the question whether mitigating the effects of rising CO2 could be offsetting the amplifying effects of warming. So I'm interested in studying process rates, as well as pools, and isotopes are really useful for both of those. My group is, bless you, my group is doing a little experiment on organic carbon priming. So on Friday, you might hear a little bit more in detail about that, but this is this idea that soil carbon can be decomposed more easily and then release nitrogen for increased plant uptake. Okay, so soils store more carbon than the atmosphere and biosphere combined. What a cool picture. There's similar maps like this in Australia, actually, but this is a little bit more familiar to most northern hemisphere people. So the dark colors are high carbon, the light colors are low carbon. You guys see some patterns in there? What explains some of those patterns? Vegetation,
Precipitation.
Precipitation, right, good, precipitation. And so in what way? Yeah, wetter places have more soil carbon, that's true. And so there's a couple reasons for that. One is that the soil carbon that stays wetter, if it goes anaerobic, it's preserved for longer. Wetter places are also have higher NPP, net primary productivity, and so there's higher input rates. So soil organic carbon accumulates in places that tend to be pretty wet, like this is the upper Midwest, which has a lot of, this is sort of the Corn Belt actually, and there's a lot of really highly productive soils there. Pacific Northwest. What about down here? What's that? The Everglades, right. So it's highly productive and it's also anaerobic. It's a wetland area, so there's peat that's accumulated there. Over here we have low carbon because the desert Southwest has low NPP and also high temperature, which can lead to decomposition rates. So low input and high output rates in these low carbon areas.
What about Texas?
What about Texas?
I mean, like in general, but specifically.
So okay, we could. This could be a long conversation, right? But so you know the 100th meridian. Have you guys read that book by Wallace Stegner? Awesome book. East of the 100th meridian, it's much more, it's much wetter, it's much more humid. West of the 100th meridian, it's much more arid. Okay, so we've got more, more mesic systems, and this whole belt gets a lot of summer rain. There's a lot of grasslands and also fires. Okay, and so fires tend to, they do release a lot of carbon, but they also create charcoal that is preserved preferentially in soils. So there's a combination of processes that go on. Does that kind of help get at the weirdness of Texas? Indeed. So, oh yeah.
I'm not from the US, but
I know.
about the Rockies?
In the Rockies.
Yeah.
So the Rockies, so where are we? Right over here. So the Rockies, it's kind of patchy in this whole intermountain west. So the mountains tend to be more productive, cooler, so there's more inputs and fewer outputs. So the mountain areas tend to accumulate more carbon, but the basin areas are drier and hotter. So that's where and they're kind of all interspersed through this whole part of the western US. And so you get that patchy.
So in mountains, you have like more carbon.
In mountains, you tend to have more carbon, right? Yeah, wherever there's higher productivity and lower decomposition rates, you'll have more carbon. Okay, awesome. So yeah, so we're thinking about not just the map, and not just the pools or the stocks that are in the soils in the ecosystems, but we're also thinking about the processes that are putting them there.